Here's a dimensional analysis question which is a bit more applied than what you're used to. So in most cases, we would just apply Buckingham Pi theorem to find a relationship between all the variables that are involved. But in this case, we're going to use that relationship straight away, and we're going to look at some applications of the Buckingham Pi theorem in real life. So here's the question. We're going to start by looking at not at an aircraft or a car or a ship, but we're going to look at a copepod, which is sort of a small crab, which has this diameter. And the goal here is to find the drag force on this copepod when it moves in fresh water. Okay, and there's an experiment done in this regard. And the experiment involves using a scale model, which is 100 times larger, right? Because the actual creature is very tiny, it's 1 millimeter across. And the test is being done in this case in glycerin at this speed right here. And the drag that you're measuring in your, not really in the wind tunnel, but in your lab, let's say, is 1.3 newtons. And the question is, well, what's the drag for one, and also what's the velocity as well of the actual copepod moving through water. Okay, so let's write a few things first. First of all, we have the density of the water, which is 1,000 kilograms per meter cubed. And in addition to that, we also have to use the density of the glycerin, which is, let's write it here as 1263 approximately kilograms per meter cubed. Okay, and other than that, we're also going to use the viscosities. So we're going to use the viscosity of glycerin as, actually, let's write it down here. So this is going to be 1.5 kilograms per meter times second. And then we're also going to use the viscosity of water. So the viscosity of water, the dynamic viscosity of water is much smaller than that. And it's about this much. Okay, so those are some of the parameters that we're using for this problem. So if the experiments are done in similar conditions, it means that the non-dimensional parameters should be equal to each other. In other words, it means the Reynolds number for the water, or the Reynolds number for the experiment, is the same as the Reynolds number in real life. Okay, so let's try to find out this here, and then once we know this, we can use that to find some of the things the question is asking about. So the not the real life, but the experimental Reynolds number, which is the same as the real life Reynolds number, is given by the density of the glycerin times the velocity of the glycerin times the diameter of the model divided by the viscosity of the glycerin. Okay, so we've got 1263 for the density. Then we have the velocity of the glycerin, which is 30 centimeters per second, or 0.3 meters per second, times the diameter. So we know that the creature has 1 millimeter in diameter, and the model is 100 times larger. So the model is going to be 100 millimeters in diameter, which is the same as 0.1 meters. So this dE is going to be 0.1 over the viscosity of the glycerin, which is, we said, 1.5. Okay, and this is going to give us the Reynolds number. So we've got 25.26 for the Reynolds number, so which is relatively low if you think about it. So let's use this to find some of the things that we don't know. So if you think about it, this is equal to the Reynolds number in real life. And the Reynolds number in real life is based on the properties of the water and on the properties of the crustacean. So we've got density of the water times the velocity of the water, now which that's the thing we don't know, times the diameter of the cope pod over the viscosity of the water. So from this equation, the only unknown, if you think about it, is this. Okay, we know everything else. We know the density of the water, we know the viscosity of the water, we know this is 1 millimeter, and we know this because we just found it here, and we know the whole situation is the two cases are dynamically similar. So we've got 25.26 for this. So let's rearrange to find the water velocity. So that's, if we cross multiply, we have 25.26 multiplied with this, which is, we said, 0.001 over water density, which is 1,000, multiplied with this, which is 1 millimeter, so 0.001 meters. Okay, so now we can cancel out those two. So the velocity of the water is 25.26, which was the Reynolds number, over 1,000. So we should have 0.02526 meters per second for the water velocity where this creature is moving. So this is, let's write it as 2.53 approximately centimeters per second. Okay, and that's the velocity. Now the other thing we can also try to find is the drag. So we know the drag acting on the model, which is about, I think, 1.3 newtons. Yeah. So we can find the drag coefficient. So the drag coefficient is drag over, and then we're just going to write the non-dimensional form of drag, which is rho, and then we have v squared times, let's write this drag because we're using diameter here, times diameter squared. You may notice that I didn't put the 1/2 here because it doesn't really make any difference because it's going to cancel out in the end, as you'll see. So let's find out what the drag coefficient is for the experiment. Okay, so let's put some extra subscripts here. So this is the density of the glycerin, the velocity of the glycerin, and it's the diameter of the experimental model. Okay, so this is 1.3. That's the force. We know the density is 1,263. We know the velocity of the glycerin is 0.3, and then we square it. And the diameter, we said it's 0.1, and we square this again. Okay, so this is going to give us the drag coefficient. So let's see how much we get for this. Okay, so we get almost, it's about 1.14. So because of dynamic similarity, this drag coefficient, this non-dimensional drag, is the same as the drag coefficient in real life. So for the drag coefficient acting on the actual creature, we have the drag acting in the real life over the density of the water, and then we have the velocity of the water squared, which we found from the Reynolds number previously, and then times the diameter of the thing squared as well. So the goal here is to find this because we know what this is. It's what we just found. It's 1.14. Okay, so the drag acting in real life is the density of the water. So I'm just going to cross multiply everything times the velocity of the water squared, which has quite a low value. So 0.02526 squared times the diameter, which was 1 millimeter, so that's 0.001 squared, and then times the drag coefficient, which is 1.14. So this should give us, let's see, quite a low number I'm expecting because of so many decimals being, yeah. So we have a very low number as 7.27 times 10 to the minus 7 newtons. Okay, which is a very low force, but it's something you would expect because this creature is really small, right? It has 1 millimeter in diameter, so you would expect uh, the the poor guy to experience a very small force as well, which that's true. Okay, so you have this force in the lab of 1.3 newtons, and the actual creature is experiencing the force of 7 orders of magnitude smaller, almost. So yeah, this is how you do, this is how you practically apply dimensional analysis in, real life or in problems. After you use the Buckingham Pi theorem to figure out what are your non-dimensional variables to begin with. And that's it. That's the end of the question.